Let's move ahead. Let's solve this problem, which deals with cooling and dehumidification. So we have moist air at 30 degrees Celsius and 50% relative humidity, which is entering a dehumidifier. Okay. So when you see this word dehumidifier, it automatically means that you are going to reduce the moisture content. Okay. So basically, the omega at the exit, omega 2, should be smaller than omega 1. If it's not the case, there's a problem in your calculation. All right, so we have moist air at this condition entering a dehumidifier, which is operating at a steady state, and the moisture is entering the dehumidifier with a volumetric flow rate of 280 meter cube per minute. Okay, this is the volume at which it's entering. Now, the moist air passes over cooling coil. That's where the dehumidification happens, and the water vapor condenses. Okay, this is expected. The condensate, meaning the water that got condensed, right? The condensed water, it exits the dehumidifier saturated at 10 degrees Celsius. So the water that's coming out, right? The water that got condensed, it's coming out in saturated state at 10 degrees Celsius. So we're saying that it's saturated liquid at 10 degrees Celsius. So you know where to get the enthalpy from, right? It's HF at 10 now. Even if this is not mentioned that it's saturated, you can assume it to be saturated because it's going to be saturated in almost all scenarios. Okay, so that's one point done. Now, what the rest of the question, let's see what it says. So then saturated moisture, okay, we also have to worry about the moisture that comes out, which is dehumidified. Okay, so saturated moisture exits in a separate stream at the same temperature. So what's the temperature? 10 degrees Celsius. So this stream is also saturated. So saturated meaning phi is 100%. The relative humidity is 100%. The temperature is 10 degrees Celsius. So we have sort of enough information to locate the state as well. Okay. Now there's no loss of energy by heat transfer to the surroundings, and pressure remains constant at 1.013 bar. So this is 1 atmospheric pressure, that is. We need to determine the mass flow rate of dry air in kilogram per minute. Okay, first part. The rate at which water is condensed in kilogram per kilogram of dry air that flows through the control volume. So we don't want just m dot w, we want m dot w divided by m dot a. This is a quantity we are interested in. Okay, and lastly, we need to calculate the required refrigeration capacity in tons. So this is the key part right here. Okay, so from here, we're going to get the cooling capacity that's needed to meet this this cooling and dehumidification application that we are looking at. Now, in this chapter 12, as we said, we're going to deal with what conditions are needed, or how do you need to play around with the moisture to make the things comfortable, right? So once you do that, you'll be able to calculate how much heat you need to reject. And once you know how much heat you need to reject, you can apply the concepts of chapter 10 to calculate how much should be the compressor power, what should be the COP, and how does the entire cycle works. You can worry about what should go within the cooling coil. Okay, you can worry about the properties of the refrigerant. For now, we are looking on the other side of the cooling coil. All right, in chapter 10, we looked at how to play with the refrigerant, how to deal with the refrigerant. Now we are looking at how does the refrigerant affects the thing outside, which is the main point of the refrigerant itself. So if you want to look at the psychrometric chart, this is how it looks like. You have state 1 right here, 50% relative humidity, 30 degrees Celsius dry bulb temperature. That's our state 1. For state 2, we know that it's saturated, so it must be somewhere on this orange line. Okay, and we know the dry bulb temperature is 10 degrees Celsius, so you can locate state 2 directly. Now, one thing that we can really clearly say is that omega 2 must be smaller than omega 1 because we're doing a dehumidification process. We're reducing the moisture content. All right. So now let's go and start solving this problem. Let's start with part A, the mass flow rate of dry air. Any suggestions? How do we calculate the mass flow rate of dry air? We have been provided the volume flow rate.
Volume flow rate over a specific volume.
Exactly. That's what we need to do here. There is a let's say a small twist, although in the way we calculate the specific volume. All right. So just as we have discussed before, if you want to calculate the mass flow rate from volume flow rate, you got to divide the volume flow rate, which is this part right here, you need to divide it with the specific volume. Now we need to divide this by the specific volume for air. Okay, so specific volume is simply R T1 by P1. But here we can't use the pressure for the entire mixture. We need to use the pressure for the air component, right? The pressure for dry air, because we're trying to determine the mass flow rate of dry air. Okay, so it's RT1 by P1 air. Okay, we are not looking at the overall pressure. Now, the reason why we are taking the overall volume, the mixture volume, but only the partial pressure of air, it's simply because this is how it comes from the Dalton's law of additive pressures, right? Which says that if you're having a mixture, right? So the mixture should be at the mixture can occupy a mixture volume and be at the mixture temperature, but the pressure for the mixture is going to be equal to the pressure of individual components. So PA plus PV. So basically, we don't want the entire mass flow rate. We only want the mass flow rate for dry air. So if you consider the mixture, if you think you can imaginarily separate it into dry air plus water vapor. Okay, so DA stands for dry air. So basically, we are looking for mass flow rate of dry air. So this is going to depend on the partial pressure of dry air. Once you add up the partial pressure of dry air to partial pressure of water vapor, we're going to get the total flow. Okay, so this is one way of looking at it. This is the concept behind it. But if you don't want to go into too much conceptual part, remember that if you trying to calculate the mass flow rate for dry air only, right, not the mass flow rate of the mixture, then here in the calculation you need to put partial pressure of dry air. Okay, now we don't have the partial pressure of dry air, we have the total pressure for now. But we know that the total pressure P1 is consists of two parts, PA1 plus PV1, right? The partial pressure of dry air plus partial pressure of the water vapor. Or you could write PA1 as P1 minus PV1. Now P1 is given, it's 1.013 bar. PV1, which is the partial pressure of water vapor in the air at state 1. This is not directly given, but we can calculate it based on the information that we already have. Okay, now we have the dry bulb temperature and we have the relative humidity. We can make use of the definition of relative humidity, which basically is phi is PV by PG, where PG is saturation pressure at the temperature of our interest. So here the temperature of our interest is 30 degrees Celsius. We can get saturation pressure at 30 degrees Celsius. So we get PG. We are trying to determine PV, but we already know phi. So we can plug in into this equation right here. Okay, we can plug into this equation where PV is relative humidity times PG, and PG1 is nothing but P sat at 30 degrees Celsius. Okay, so this is by definition, right? So we have relative humidity 50% or 0.5 times this saturation pressure, and this is how we multiply them to get PV1. So as expected, PV1 is rather small, right? The amount of water vapor within the air is not so high, it's small. But this is the value that we have for PV1. Now we can go back and calculate PA. So PA1 is 1.013 bar minus this value minus PV1. It comes out to be 0.99177. It's pretty close to 1 bar, but it's smaller than that, right? I mean, we have to use this exact value to calculate the exact mass flow rate of dry air. We obviously know that the mass flow rate of dry air is very close to the mass flow rate of the total mixture, but if we take the mass flow rate of the total mixture, it's going to result in errors, right? We're going to get a higher value than what we should. So for accuracy, this is how we do it. And now that we have the partial pressure of dry air, we can plug it into this equation right here. Of course, when we're writing it, mass flow rate of dry air, we have the volume flow rate. It's given as 280 meter cube per minute divided by this R by M is nothing but the gas constant for air, which we know is 0.287 times temperature. We need to use that in Kelvin. So 30 is 303 Kelvin divided by the pressure, right? I can put the pressure at the top. So when I put the pressure at the top, I need to convert that into kilopascal. So I multiply 0.99177 bar into 100 so that it's converted to kilopascal. So this part is something that you have done several times before. And this is exactly what we need to do here. When you do the math, this is what we get. So the mass flow rate of dry air is calculated. That's part A done. So this is going to be done in exactly the same way as you did before. The only difference or the key difference is that we have to use the partial pressure for dry air, and we have to do a couple of steps to calculate the partial pressure of dry air. Okay, that's part A done. Now let's look at part B. We need to calculate the rate at which water is condensed in kilogram per kilogram of dry air. So we want mass flow rate of water by mass flow rate of dry air. So how do we get that? What is the concept here? How do we calculate how much water got condensed?
It is the change in the omega.
Exactly. Excellent, Abdul Hamid. So omega indicates how much moisture is there in the air, right? So the difference in the omega simply tells you that we have lost some moisture, we have lost some water, and the lost water, the water which is lost from the vapor phase is simply going into the liquid phase, and that's all what's happening. So here, m dot water by m dot air is simply omega 1 minus omega 2. Now, if you want, you can also get it from the mass balance, right? So I could write it as the mass of water which is entering at state 1, m dot v1 is equal to mass of water that got condensed plus mass of water vapor at the exit, m dot v2. Okay. Now you can write this part as mass of water vapor as mass of dry air times omega 1, which be equal to m dot w plus m dot a again times omega 2. Now we are not interested in m dot w, we are interested in m dot w by m dot a. So you can divide all of this and then send this part to the left. Okay, so you have omega 1 minus omega 2. You get this from mass balance if you are not sure about what's happening conceptually, but otherwise, if you understand what's happening, it's simply omega 1 minus omega 2. The difference is what it is, right? So you can get it from mass balance here if you like, but you eventually end up with this. It's the difference between the omegas, right? If there's no difference between the omegas, you did not do any dehumidification. You basically stopped at the dew point temperature. So here we need to only calculate omega 1 and omega 2. And calculating these two is pretty straightforward. There are formulas that are already available in your formula sheet. You just need to know how to apply them. So omega 1 is 0.662 times PV by P1 minus PV. What's P1 is the mixture pressure. It's this pressure 1.013 bar. It's already known. PV1 we already calculated it, right? It's related to the amount of water vapor in the air, and we calculated it using the relative humidity and the temperature that we had. So you plug in these numbers and this is the value that we get. So you can see this omega 1 value is a little bit higher than normal, right? Normally we have 0.006 around. I'm not saying this is the value every time, but this is somewhere the value that you would have for air which is relatively, let's say, less humid, right? But here we have a pretty high moisture content, so we need to sort of reduce that. Now, this is how you would calculate omega 1. For us, we also need to calculate omega 2. Omega 2 is going to be calculated using the same process, right? Omega 2 is going to be 0.622 times now PV2 by P2 minus PV2. Now there's no change in the pressure, right? The pressure is going to remain constant. So P1 is equal to P2. Okay. Now PV2 is basically the partial pressure at state 2. We know that at state 2 the air is completely saturated. So it's PV2 is nothing but it's Psat at 10 degrees Celsius. Okay. So we go to the table, get the value of saturation pressure in 10 degrees Celsius, plug in the numbers here. Once you do it, this comes out to be 0.0076. Okay, so this is the value that we get for omega 2. Now we have omega 1, we have omega 2. It's a matter of plugging into this equation right here, and omega 1 minus omega 2 gives us the amount of water that got condensed per unit mass of dry air. So this is the water, the amount that got condensed. Basically, you could think of it as almost about 40% of the initial water got condensed, right? 40 to maybe 50%, slightly less than 50% for sure. Okay, so this is the second part. Any questions in part A and part B?
Doctor, is it possible to find omegas from the chart?
Excellent point. I was going to discuss that as well. So in this question, there's no mention of the chart. So if there's no mention of the chart, well, you got to solve it using the using these formulations. But here, if any point in the question they said use the psychrometric chart, then you can go ahead and use the psychrometric chart for determining omega 1, omega 2, omega 2 here. And also, if you want, you could also sort of get the volume for air directly from the chart itself, right? I mean, that's sort of given to you, but if you wanted to find out the volume or enthalpy, you can get it directly from the chart. I'm going to show you how you would solve this problem with the chart as well. But yes, you need to have this wording in the question. If the question does not say use a psychometric chart, you can actually use it. So this is part one and part two. If you have any other questions, let me know. Otherwise, I'll show you how to calculate omega. We'll just show how to look at omega 1 and omega 2 from the chart. You already have done that, you know it, right? So this formula is something that you would bring. You'll stop here and then you get omega 1 and omega 2 from the chart. Any other questions apart from that? Okay, so if the question says use the psychometric chart, well, you're going to make use of that. So state one is 30 degrees Celsius and 50% relative humidity. So this is the dry bulb temperature we're looking at, and 50% relative humidity. So this is our point. This is our point of concern. You just draw a line. It comes out to be 0.013. Of course, it's not going to be 0.0133. That's okay. So you use this value for omega 1. Now for state 2, it's saturated. So we just have to make use of the dry bulb temperature and reach here. So this is our point. So you draw a line all the way here. Sorry, should have followed this line at the bottom. So when you draw this, it comes out to be somewhere between, this is 0.007, somewhere between 0.007 and 0.008. You can take it as 0.0075. It's not going to be 0.0076. There will be minor differences, but that's okay. Okay, so you could pick up the omega 1 and omega 2 values from here, but you can do this. You should know, but if you want to calculate m dot w, you should know the relationship between them, right? You should know that m dot w by m dot a is omega 1 minus omega 2. So this is how you would do it using the psychometric chart. Now let's solve the last part of the question, and then I will again show you how you would do it using the psychometric chart. Now we need to calculate the required refrigeration capacity, or how much heat needs to be rejected. How do we do this? Any ideas? Do we apply? Yes, go ahead, Abdul Ahmed. You want to add?
Energy balance?
Yes, energy balance. Nothing new, right? We just need to apply the energy balance here to calculate how much heat needs to be rejected. Now here, this is the general form of the energy balance, and here when we write Q dot CV, by default it's Q dot in, but we know that we are rejecting, so the answer at the end is going to be negative. Now it just has, I mean, there's no work output here, right? Obviously, so we just have to consider the mass times the enthalpies for the different components. So this is what's entering, and then these are the two streams that are exiting: condensed water plus moist air. So first we're going to look at how can we solve it from the tables. Okay, so we are trying to determine Q dot CV, so we can sort of put all other terms on the other side of the equation. And there's one more thing that we can do here. Here we have everything in terms of mass flow rates of individual components. We like to have mass flow rate of dry air. That's okay. But mass flow rate of water vapor is something that we would want to convert that into a form which is something times dry air. And we know that mass flow rate of water vapor can be written as omega times mass flow rate of dry air. So this is omega 1 times mass flow rate of dry air. And here this is omega 2 times mass flow rate of dry air. Okay, and of course m dot w, either you could calculate it and put the value directly, or if you want to write it into this equation, you could also write it as m dot a times omega 1 minus omega 2. Okay, so we can make use of this and write the following, rearrange this equation, sending q dot cv on one side and everything else on the rest. So since m dot a is common across all the three terms, you take m dot a out, and then you can arrange the terms to bring similar terms together. So you have Ha2 minus Ha1, increase in the change in enthalpy of the air, minus omega 1 times Hg1. Hg1 is basically enthalpy at temperature 1, 30 degrees Celsius. Then you have plus omega 2 times Hg2. This is at 10 degrees Celsius. Plus omega 1 minus omega 2 times HF2. How did we get HF2, or why are we getting HF2? Well, we want enthalpy of water, and we know that the enthalpy of water, we know that the water comes out at saturated state, so we're going to take HF at 10 degrees Celsius. So we're referring it to because it's coming out at state 2. Okay, nothing else. So these are the three different enthalpies, Hg1, Hg2, and HF2, which you get from table A2. The only other thing is the enthalpy for dry air. You can get it from table A22, or if you want to save time, you could just write it as Cp delta T. The value of Cp would be 1.005. It's your choice. Both methods, I'm going to give you full marks. Okay. So here we know already what the mass flow rate of dry air is. We calculated in part A. So you plug in these numbers here, and these are the enthalpies for dry air. This is the enthalpy for saturated vapor at the two temperatures, and this is HF at 10 degrees Celsius. You plug in the numbers and it comes out to be negative of something, right? And it's simply negative because heat is being rejected. There's no heat coming into the system. Now this is in terms of kilojoule per minute, simply because we had the mass flow rate in kilogram per minute. Okay, we are not interested in this unit of kilojoule. We want it to be converted to tons. So 1 ton is equal to 211 kilojoule per minute. So you sort of divide this by the number. You divide 11,000 by this 2 on 1, and we end up with a cooling capacity of 52.5 tons. So this is what we were interested in. Okay, so this is a pretty large number, right? So just to give you a physical feeling for this, the air conditioners that we have in our houses, I mean, if you have, let's say, the window or the split air conditioning system, the larger versions typically have cooling capacity of 2 tons. Okay, so let's say if 2 tons is enough to cool one large room, we are basically having 52.5 tons. So basically, we are having enough cooling capacity to cool 26 large rooms. So you can imagine this is either a very large auditorium or a conference center, or maybe an entire building, right? An entire building which has these 26 rooms. So the problem that we solve here is basically with the mass flow rates and the stuff that we considered. It's enough to meet the cooling needs of an entire building as well. Okay, so this is how you would solve it if there's no mention of the psychometric charts. If the question mentioned use psychometric charts, then we sort of use this equation and we keep this component, right? We keep this component right here. So because in the charts we have the enthalpy for the mixture. All right, so you just have to take m dot a out common. I take m dot a out common and then write HA plus omega HV, which represents this part right here, minus HA plus omega HV at state 1. These two, HA plus omega HV, is what's given here at state 1 and state 2. You pick it up from the charts. And lastly, you just need to write omega 1 and omega 2 times HW. HW again is HF, which you get it from table A2. So you just need to get one value from table A2. Everything else you can get it from the chart, omega 1, omega 2, and this enthalpies for the mixture. Okay, you can do this yourself and check out the answer. The answer should come out to be almost similar to this, maybe 11,000 something.